Hi, my name is Tianjian from Johns Hopkins University. Today I will be presenting our work Error Norm Truncation, which is about locating and removing data errors for training language models. Here is a common pipeline of our model training. We feed the vast amount of data we have into a neural network. If we zoom into our training data, we can see that there are some errors. In this case, in a summarization dataset, there are certain details in the ground truth summary that are not supported by the input passage. The ultimate question that we would like to ask is that how does these data errors affect model training? We look into this from a theoretical perspective. The autoregressive maximum likelihood objective breaks down the sentence probability into sums of log probabilities of individual tokens. Taking one step further, if we calculate the gradient with respect to a single token, we see that when the predicted probability of the token is small, the magnitude of the gradient goes very large. This indicates when a noisy token has very low predicted probability or high loss, this leads to a very large gradient update to an undesired direction. However, a low predicted probability does not necessarily indicate noisy training data. For example, it could be the case that the model encounters a high entropy context and distributes the probability mass to synonyms, leading to a low predicted probability of the ground truth token. It could also be the case that the model is at the beginning of training, has never seen similar context during training, and thus uniformly assigns probabilities to all possible tokens. Contrastively, when the model is certain that a token is wrong, it assigns a high probability to another token. So ideally, we want to incorporate loss plus skewness of the probability distribution over the non-target tokens to differentiate between the first two cases and the third one. What we propose is to use the error norm. It is very simple. The difference between the predicted probability distribution and the one hot target distribution, and we take the L2 norm of this difference vector. We see that although all three cases had the same loss, the error norm of the third example is much larger and distinguishes between clean and noisy tokens. We validate our method empirically. The left line plot shows that when we are pre-training a model from scratch, in this case we're pre-training a GPT-2 large model on Wikitext 103, the error norm only gets larger after an initial warm-up phase, meaning that the model learns to distinguish clean and noisy tokens on the fly. The histograms on the right shows clean and noisy text in blue and red color respectively. And we see that the right histogram, which is the distribution of the error norms, more clearly distinguishes between clean and noisy text compared to the middle histogram, which shows the loss distributions. Furthermore, we inject various amounts of noise into a machine translation dataset. We find that the performance decreases a lot as we inject more noise when using the maximum likelihood objective. Existing work based on filtering high loss training data only yields minor improvements. Our method, Error Norm Truncation, achieves the best performance, especially at higher noise levels. We also apply our method to pre-training language models from scratch. Although loss filtering can improve upon the baseline, they are often very sensitive to hyperparameter configurations. Our method achieves the best performance while being the most stable under different hyperparameter configurations. To sum up, the takeaway is that the training data is often very noisy, and the commonly used training objective is vulnerable to this kind of noise. The commonly applied removing low probability tokens is limited. It leads to an inaccurate estimate of token quality. Our method, on the other hand, the error norm, clearly separates between clean and noisy tokens and results in improved downstream performance. So, either if you're pre training or fine tuning a language model on noisy text, you may want to use our method because it improves the performance with incurring minimal computational overhead. There are more results in our paper, and please check it out. Thank you very much.